Okay, so we're going to be looking at Module 7. Module 7 is our last module in this course, and it's dedicated to mechanism design. So up until this point, we've really kind of been given a diagram and in all the dimensions on it. Now we're going to kind of, if you would, reverse engineer. We're going to start from what we want our output to be, and now you're going to have the chance to, with some parameters and some quantities and variables that we need to keep in mind, you're going to get to now design the actual mechanism itself to accomplish a job, if you would. So in Module 7, if we look at our learning plan, we are going to be following along with this PowerPoint. It's a Chapter 5 PowerPoint. I'll be pulling that up in just a little bit. So Chapter 5 is where we're going to be getting all the, if you would, context out. I will have our session recordings posted in Module 7, session recordings, so nothing to look at there right now. But you'll notice that we have practice problems and assignment number 7. If we click on the practice problems, we have 4 practice problems that we're going to be doing. Example 5.1, which is right out of the book. But then we're going to be doing 3 problems. For some reason in this chapter, they didn't go over actual full problems in the example. So I picked out a couple problems from the end of the chapter that are going to mimic the assignment problems that you're going to have. So it's really intended to give you a nice demo on how you're going to be doing your homework problems. So there's going to be 4 practice problems here. And then we have assignment number 7, and it looks like there's about 6 problems here. The first 2 are a little bit shorter, and then the last 3 are a little bit longer. So you'll notice that there's more points associated with the last 3. But by the time we get done with our chapter here, you'll have everything that you need to know to get that done. Okay? So let's go ahead, and I'm going to pull up the PowerPoint presentation here in the learning plan. I'm going to zoom out here a little bit, and we're going to kind of get started here and kind of think about some things before we jump in. So first of all, it says here, we've been studying and we've been looking at a number of 4-bar mechanisms and slider crank mechanisms. There have been what we've been kind of, living with, if you would, and looking at them in a lot of different ways, not only kinematic diagrams or looking at displacements, but we're looking at velocities as well. And I want you, it's been a little bit since we have worked on these types of kinematic diagrams. I want you to just take a minute, 60 seconds, to list as many applications of a 4-bar mechanism and a slider crank mechanism that you can think of. So just get out a piece of paper, and just for your eyes only, but, kind of remembering, I've got 2 kind of basic diagrams down here of each 4-bar mechanism and a slider crank mechanism. Think of, these are those stripped down kinematic diagrams, simplified versions that we see. What are some real world applications, some of the diagrams that we did and such that you can think of for these 4-bar mechanisms? There's not a minimum number here. It's just, to kind of jog your memory for some applications of these 4-bar mechanisms and slider crank mechanisms that we've been looking at. Now, once you've generated a list based on your memory and your experience, then I want you to take one more minute and do a quick Google search of different applications of 4-bar and slider crank mechanisms to add to your list. So go ahead, and if you want to, do it on your computer or on your phone, Just do a quick Google search of different 4-bar mechanism applications. See if you can find any that you didn't think of. Right. Okay, let's just generate a little bit of a list here and see what you guys came up with. So I'll start in the room. Anybody want to share one of the items that you have on your list for 4-bar mechanism slash, I mean, in a slider crank is also a 4-bar mechanism. So either one of those, any applications, I'll write them down. Liam.
A linkage control and a manual transmission.
Manual transmission, yes. What else? I'll do another one in the room here, and then we'll go to virtual. Air compressor. Yeah. The mechanism to generate the actual pressure, right? Air compressor. Great. And that would be a slider crank, right? Yeah, absolutely. How about virtually? If you guys want to put in the chat box, or if you want to say it. Oh, locking pliers. Okay, great. Yeah. An oil pump rig. Excellent. Okay, what else? Anybody have something else on their list? I know there's more than 4 people in our class. Liam.
A-frame ladder.
An A-frame ladder. Yes. And then I saw Emily added can crusher. Oopsie. Yes, a can crusher. Absolutely. And Tyler has a Sawzall. Is that right? Yeah. Others. Who hasn't shared yet? Oh, Ariasto, bicycles. Yeah. Okay. What else? Who else? Oh, I've got skid steers. Okay. A human knee joint. Yeah. Yeah. I like it. Human. Anybody else want to share something that they riding a bike? Yeah. Anybody else want to share something that you maybe have on your list that's not on here that you're like, I think this is a good application? A piston connecting rod. Absolutely. There's our kind of our standard classic example, right? Yes. Now, what was that?
Door latches.
Door latches, sure. They're all over, right? Now, as we look at these applications, these are things that, many of them that we've run into in our everyday life, right? And then we experience. Now, think about the person who, if you would, designed that product, okay? Before, they had the final product in their hands or in the final application, what are some of the things that you think you have to think of? Like, what are the variables in the design, okay, that have to be thought about in many of these things. You know, like what is something that you have to probably like before you even get into, you know, materials, for instance, or the forces, right? And on the kinematic side of things, what are the variables that you think are going to be considered for any or all of these items? Maybe not the human knee joint. Liam.
Space or volume allowed.
Look at that. Tyler and Liam said at the same time, your space constraints, right? So what is the, if you would, the box that we have to fit it inside of, right? And what are the areas that we can't go outside of, right? So what's that envelope look like that we have to design within? Yes, absolutely. Space is going to be part of it. What else?
Weight constraints at this point.
Yeah, I mean, I wouldn't say not at the kinematic level because remember, weight is going to be part of materials and forces, so that would be just a little bit down the line. But when we think about layout, we think about space. That's one thing. What else are we going to think about? Ben, yes, where are the joints going to be? Where are they going to come together? What types of joints, right? What types of joints? So placement and types. Yes, absolutely. Because is it a sliding joint? Is it a pin joint? Hmm. What else? Movement limits. Yes. What's the type of movement that needs to be required? Is it going to be rotational, right? Because we've experienced rotational, but we've also seen translational or linear, right? Where with a piston, it's going to be going in a linear fashion where then we have to have a crank that's going to be going rotationally. So our input is going to be rotational, um, our output is going to be linear. But in the case of a crank rocker, well, now we've got a crank that's going to be going around and we got to know what the rotational is. And then also what is the oscillating that's going to occur. Contact points. Yep. And I'm gonna lump that Emily into joints here. And then, oh yeah, what are the other types of movement that we could have? Can we incorporate gears or belts? Oops, belts or chains, right? And then what are the ratios? Yeah, absolutely. For each one of those, right? The different types. What's going to be what's going to be the one that's going to make the most sense to incorporate, right? And we saw different applications of that. Anything else that you can think of that are going to be variables that you have to consider as you're creating your design?
Budget.
Yeah, budget. Always. Volume, absolutely, yes. And I guess we don't think of that because normally we are looking at 2D in terms of where we're doing it with our what we're doing with our kinematic diagrams. But there is depth there, right? Like how thick is that going to be or how deep? So yeah, that would be considering the volume, another dimension, if you would, for the space that we have. All right. Any other things that you can think of? I think you've exhausted most everything I can think of, at least in the kinematic side of things, what we want to consider, when we're looking at any type of mechanism that we want to design. Okay. So thank you. That was good. That was good. And we kind of talked about this as well. We each shared, some things for our list. And we did that already. We made the list. Okay. So let's look at mechanism design, and this is going to be chapter 5. So today, I like to say we get to learn how to use graphical methods to initiate the design of mechanisms. Okay, there are going to be some calculations and some things that we have to consider as we start this process. But for the most part, we're gonna be looking at graphically how can we design these mechanisms with an end result in mind. Find out why it's important to know these techniques and processes, and then also start to think about maybe your capstone project course and the possible projects that you could actually work on. I know that actually do you guys have Tom right now? Yeah. What do you have him for? Yeah, do you have Tom right now? No, you don't. You don't. You had him last term, right? For the CAD class. And I know that he started kind of your wheels turning on the capstone project. But this is where too, when you're starting those initial design processes and those initial like brainstorms of what we can do, kinematics is probably going to enter into that particular conversation and what is going to be needed depending on the motion that you are going to be considering for your final project. So that's it's just here for not to make a list right now, you know, in front of the class, but start thinking in terms of that capstone project and how some of this might apply. And when we're doing mechanism design, it's a good place to kind of apply the things that we're going to be learning today. All right, so our objectives here are, first of all, to look at the term mechanism synthesis, and it's really mechanism design. It's just a fancy word for that. We're going to be looking at designing an inline slider crank mechanism. We're going to get to know what the desired mechanical time ratios are that we're going to be considering so that we have a smooth moving mechanism as its end result. Yes, Tom is going to be in your capstone course. I just saw what you put in there, Ben. Yeah, he does all the capstone courses for mech design, the mechanical engineering technology, and the manufacturing engineering technology. So he's dedicated to that in the spring. That's his thing. We're also going to be looking at using these graphical methods. I'm going to forego the timing charts. It's in the chapter, but I kind of pulled away from having you guys worry about creating those. So we're not going to worry so much about the timing charts. We're going to jump to the graphical methods here. Now, let's look at synthesis. Synthesis is basically the process of designing a mechanism that produces the desired output motion for a given input motion, okay? There's different types of or type synthesis, and this is going to be the selection of a particular mechanism that's capable of determining the desired motion. So as we had seen earlier, are we going to use a crank oscillating? Are we going to use a slider crank? Are we going to use gears, bells, chains to kind of achieve whatever it is? So figuring out what type of mechanism design or synthesis is what you're going to do very early on. In some cases, you may consider a couple of them. So for instance, you might try to determine, am I going to use belts or am I going to use chains? They kind of, you know, are similar in operation and in flexibility, but one might be suited better than the other, or you might design for both of them and then consider what the better outcome is going to be, okay? Now, dimensional synthesis is going to be determining the length of each one of those links. And that's going to be an important part of the assignments and the examples that we go through here today. Okay, so we're going to be focusing on dimensional synthesis in this lesson. So the first thing we're going to be looking at here in section 5.1 is what we call time ratio. Now, the first type of motion that we're going to be looking at in terms of time ratio is going to be what we call symmetrical motion. And that means that when we look at the stroke of a crank slider mechanism, we're going to have the identical outward stroke as we do the inward stroke in terms of timing. So if we're going to say it's going to take 1 second to slide all the way out, we're going to have it slide all the way in at 1 second as well. So it ends up being balanced on both sides, okay? Now, the nice thing about this type of a design, this symmetrical, is that it is going to give us the ability to do work in both directions, okay? So let's look at a quick video of an example of this. There we go. Isn't it going to go? Oh, here it is. It's in the background here. All right. There we go. Let me go full screen here. So this is considered symmetrical because you're going to notice as we look at the slider here on the outbound to the inbound, if you compare how fast or slow that this is going, it's even in both cases. Okay, it's even in both cases. Actually, I'm going to make this small. You'll also notice that they changed the view here, but the center of the crank is in line with the path of the slider. Okay, so this would be an inline slider crank mechanism. Okay, so this center right here is in line with that path. That's it. There's my little stop button. There we go. So that's an example of symmetrical motion. It's covered here. There we go. Okay. Now, the next type is called a non-cylindrical or non-symmetrical, I'm sorry, non-symmetrical motion. And this is where we have something that's called like a quick return. So we do work in one direction, which is going to be the slower side of the stroke, but then we come back very fast. So things like cutting machines or packaging equipment, they'll move in one direction and then they'll come back real quickly to kind of get back into position to then move another product. So I have another little video here for a quick return. Right here. So up here, you're going to notice, and it's very kind of slight, but as it comes to the left, it's going to be slower. And then as it goes back to the right, it's going to be faster. Okay. So this is called what we would call a quick return. So the work, if you would be done in one direction, and then it would come back more quickly to then start that action over again, that work cycle to occur again. So this is a non-symmetrical. Now, there are some equations here that are going to help us kind of set things up for each one of these cases. And I'm actually going to go to the bottom of the second column on page 109 in our book. We're going to find these elements that are in that PowerPoint. And they're also going to be the ones that we're going to be using and calculating for not only our practice problems, but also for the assignment that you're going to end up having. So what I'd like to do is it's going to come in handy when we do our practice problems as well as our examples is to kind of create an equation sheet for us. So I'm going to start by, go out here a little bit. This is going to be my mechanism design equation sheet, okay? And I'm just going to say that this is chapter 5. We do a lot of equation sheets. I think it's nice to, number one, kind of bring them together in one place so you don't have to be paging through. But also as we write these out, I think they stick in your mind a little bit better too. All right. So as we look here, the first equation that we're going to start with, it's going to be called Q. Okay. And Q is going to be equal to T1 over T2. Okay. That's how we calculate it. And its value is going to be greater than or equal to 1. Okay. Now, Q is called, and I'm going to kind of go over on the right-hand side here. So we'll do our equations on the left-hand side. On the right-hand side, we'll kind of identify what each one of our variables are. So Q is called time ratio. Okay. And because it's a ratio, okay, we're going to have time on top and on bottom. There are going to be no units here. So it's just going to be a ratio. It's just going to be a number. Okay, so no units here. Now, T1 is going to equal the time of the slower stroke. Okay, and those units are going to be in seconds. Okay, as we can, it's very consistent. And then T2 is going to be the time of the faster stroke. And that's also going to be in seconds. Okay. Now, when Q is equal to 1, this is considered symmetrical. I'm going to just, oh, I can never plan out. I write bigger than I think I'm going to, metrical. Okay. So when Q is equal to 1, it's symmetrical because the time out is going to be equal to the time in. Okay. So that means T1 is equal to time T2. So then our Q is going to be equal to 1. And when it's equal to 1, it's a symmetrical motion. Okay. If it's something greater than 1, that means that our slower stroke is larger than our faster stroke. So we've got a quick return on that. So we're going to get something greater than 1 for our Q value, and that's non-symmetrical. Okay. All right. The next thing we're going to look at is the imbalance angle. The imbalance angle beta is going to be equal to 180 degrees times Q minus 1 divided by Q plus 1 on the bottom. Okay. And this is again, it's the equation at the bottom of that column. It's equation 5.2. Okay. Actually, 5.3 is this one. Now, this is only present on offset mechanisms. Okay. So what's an offset mechanism? Offset mechanism is when we have a distance between the crank center, this crank center of rotation, and in the case of a slider crank, it's going to be offset from the path of the slider. Okay. We do not have a beta when we have a Q equal to 1. Okay. If we have a Q equal to 1, all right, 1 minus 1 is what? 0. 1 plus 1 is 2. If we divide anything by or 0 by a number, what do we get? 0, right? We get 0. So beta becomes 0 when it's something that is symmetrical or inline. Okay. And these will, again, we're going to do some examples. So we're just writing down right now. Now, you should put over here, beta is going to be imbalance angle. And we'll identify that too when we start drawing things out. And that's going to be in degrees. Now our next one is going to be our total time of our cycle. And that's going to be T1 plus T2. And the book shows it as delta T cycle and T1 plus T2. So delta T cycle is equal to the total cycle time. And all that is that is going to be one rotation of the crank. How long does it take for one rotation of the crank? And then in this section, the last one we're going to do is going to be the angular velocity or rotational speed of our crank. And that's going to be equal to 1 revolution divided by that total cycle time. Okay.
W sub what?
I have crank, CR of the crank. A lot of times it's going to be link number 2, like we've been seeing a lot, but in here they call it W of the crank. So W crank is going to be the rotational speed of the crank. And that's going to be in RPM, as we know. Okay. And again, it's going to be 1 revolution divided by the total cycle time. Now, cycle time, we're probably going to have in seconds. We're going to have it in seconds. So we have to convert it when we're reporting out, if you would, what our rotational speed is. We have to convert it to RPMs. Okay. So let's do our first example, kind of using what we have here and kind of practicing these equations. All right. So our first example, and it's the first practice problem that you'll be submitting, is going to be example 5.1. Okay. It says here that we have a quick return mechanism is to be designed where the outward stroke must consume 1.2 seconds and the return stroke 0.8 seconds. Okay, so it's a quick return because when we go out, it's going to be slower. And when we come back, it's going to be faster based on the times that they have here. So when we have a mechanism like this, what that means is we're going to be doing the work that we need to do, the function, the main function of that mechanism on the outward or the outbound stroke. And then we're going to return it quickly so that we can save a little time when we're not doing the work to get back in position to now do the next stroke. Okay. And then what they want us to do here is they want us to determine the time ratio, the imbalance angle, the cycle time, and the speed of the mechanism, the speed for which this mechanism should be driven. Okay, so I'm going to grab a new piece of paper here, and we're going to do example 5.1. Okay, so I'm going to keep my equation sheet handy. Okay, so this is going to be example 5.1. Okay, and let's identify what we're given in the problem first. So it says here a quick return mechanism is to be designed where we have an outward stroke to consume 1.2 seconds. So as we look here, that's giving us a time, right? And we have two times. We have 1.2 seconds for the outbound stroke, and then the outward stroke, and then the return stroke is 0.8. So these two times right here, T1 and T2, are going to be assigned for each one of those values. So T1 is always going to be the slower amount of time for the stroke. So that means that our 1.2 compared to the 0.8, the 1.2 is going to be our slower. So we're given in this problem, T1 is equal to 1.2 seconds. Okay. Then the other part of this problem, as we look at our equation sheet, time 2 is going to be the faster part of the stroke. So it said that the return stroke is going to be 0.8. So our T2, which is the faster one, is going to be 0.8 seconds. And those are the only two things that were given, okay? Only two things that were given. So what we need to find are the following, okay? They want us to find the time ratio, and that is Q. Okay, so from our equation sheet here, time ratio is Q, and Q's equations is over here. So we'll be calculating that. So we need to find Q. They want us to find the imbalance angle. The imbalance angle is beta. That's that equation there. So we want to put beta over here. Got to find that. We need to find the total cycle time. Okay. So the total cycle time is going to be the delta T cycle. Okay. And then lastly, we need to determine what the speed of the driving mechanism is. So the speed is going to be the rotational speed of the crank. So that's going to be W crank. Okay. So just those two pieces of information were given, and we have to find 4 different things. Okay. But we're in good shape. We'll have what we need. So now what we're going to do is we're going to start by finding our Q. Okay. And we can really start with any of these, but Q is the first one there. So let's start by looking at that. So we know that Q is going to be equal to T1 divided by T2, which we have both of those. And then we're going to compare it to 1. All right. So let's calculate its value first. It's just a ratio. So Q is equal to T1 divided by T2. So we're going to have 1.2 seconds on top, 0.8 seconds on the bottom. Seconds cancel here. All right. It's a ratio. It won't have any final units. So Q is equal to, what do we get for a number for Q? 1.5. Oh, 1.2 divided by 0.8. Oh, that's okay. 1.5, yes, 1.5. And again, no units because it's a ratio, the seconds cancel. Okay, so that means that this is the first quantity that we have here, okay? The next one that we have is beta. Let's see if we can calculate beta. So if we look over on our equation sheet, beta is going to be equal to 180 degrees times our Q minus 1 divided by Q plus 1. So yes, we have the Q now. So we can use that to calculate beta. So step number 2 is going to be beta, or that imbalance angle. It's going to be equal to 180 degrees times Q minus 1 on top, Q plus 1 on the bottom. So that's going to equal 180 degrees times 1.5 minus 1 over 1.5 plus 1 on the bottom. So what do we get for our beta? And for those who are virtual, feel free to put it into the chat if you'd like.
36.
36 degrees. Anybody else get that? Sounds like a good number. Yep, I've got nods in the room. Excellent. Okay, so beta is equal to 36 degrees. So that's our second one. Awesome. Okay. The next one that we have here is going to be our total cycle time. So if we look back at our equation sheet, total cycle time, to calculate it, we just take T1 plus T2. Easy peasy. So number 3 is going to be delta T cycle is equal to T1 plus T2. Okay. So that's going to equal 1.2 seconds plus 0.8 seconds. So our delta T cycle should equal 2 seconds, right? Right. So we've got our total time. And then the last one is going to be our angular velocity of our crank. Okay. The angular velocity of the crank is where we take 1 revolution of that crank and we divide it by the total cycle time. Okay. So step number 4 is going to be our angular velocity of our crank. It's going to be equal to 1 revolution divided by change in T cycle, or the total cycle time. So 1 revolution divided by 2 seconds, right? 2 seconds, because that was from the previous step here. Now, you could say 1/2 revolution per second, but as we know, whenever we report our angular velocity, we need to put it in what? Not revolutions per second, we need to put it in revolutions per minute, right? So we have to change this to RPM. So don't leave it as revolutions per second. You have to put it in RPMs. Thank you, Emily and Ben. All right, so 60 seconds on top, 1 minute on the bottom, seconds cancel. What do you get for the angular velocity of your crank? So you would take 1 times 60 divided by 2. Yes, 30 RPMs. And go box around that. And then that's our final answer. Good. So just kind of a warm up using those equations and the terminology and making sure we kind of, can make sense of those. So we will be using these terms and these many of these calculations in the problems that we do, but then we're going to take it a step further and actually design the lengths of each one. Okay, so any questions on example 5.1 right now? Okay. Okay. So let's take a peek back at our PowerPoint presentation. So we did our equations from up here, and then we applied them in example problem 5.1. Okay. So the next thing we're going to be looking at is slider crank mechanism design. Okay, slider crank mechanism design. So slider crank mechanisms, we've hit them along the way in a lot of different applications. Very classic example is going to be a piston connecting rod in an engine. So let's take a quick look at the YouTube video I have out here of this one. Okay, so that piston is going up and down. Connecting rod is in between here, and the crank is going to be on the camshaft as we see as it goes around. So we take rotational speed, this is your input at the bottom, and we translate it into linear motion, okay? So again, very classic example, slider crank mechanism. Yes. Okay. Then the other one is sewing machine, power hacksaw. I think this is a power hacksaw in this example, if I'm remembering correctly. Yeah, it is. So this one kind of takes it a little bit step further and looks at all the different parts too, kind of pulls it apart. It's very short, don't worry. Right. So just another example. So let's look at figure 5.3 in our book and kind of look at a couple of these elements here that some of them are going to be familiar to us and some of them are going to be a little bit new. So let's look at stroke first. We have looked at stroke in terms of 4-bar mechanisms or slider crank mechanisms, but let's go underneath and look at figure 5.3 at the top of page 114. So as we look here, we have a slider crank mechanism. We have the slide right here, okay? And then the crank is over link number 2. Our frame is here at number 1, and then our connecting rod is number 3. So our conventional numbering system that we have used and applied since, I think, module 1, when we were right at the beginning of the course. So number 1 is going to be our frame. Number 2 is going to be our crank. 3 is the connecting rod. And number 4 is the slider. So when we look at, for instance, L2, that is going to reference the length of the crank. Okay. So from the center of rotation to that outermost portion here, the length of this radius is L2. Okay. Then the connecting rod length, because that's link number 3, that's going to be length number 3 or L3. Okay, so you can see here that if we wanted to figure out the length of number 3, that's going to be associated with the connecting rod. And then number 4 is going to signify our slider. Now, as far as joints, these joints will be referenced as well in some of the equations coming up. So here, starting at the crank, we have A is going to be, I think you see A right down here. A is going to be the center of rotation for our first joint here at the frame. B is going to be the end point of our crank. Again, just like we've been using since the beginning of kinematics. C is going to be the center of our slider. And they don't have D identified here because it's not really going to be referenced in anything, but D would be the connection between that horizontal plane, which is the frame, and the slider that is going to be constrained to be in contact with that. So it stays in a horizontal manner. Okay. So that, if you would, the joint numbers, I'm sorry, the joint letters and the link numbers are going to be consistent with what we've used up until this point for 4-bar mechanisms. Okay. Now, in this example, you're going to notice that the center of the rotation of the crank, if we extend it, is in line with the path that our slider takes. So this is called an inline slider crank mechanism. And we've seen these, before. Now, as we lay this out, and if you remember, I think this was module 2 for you guys. I think it was module 2. We looked at the outermost and closest bounds of what the limiting positions would be. So the furthest out that our piston is going to go is going to be out here at what we call C2. Okay. The furthest that it's in is going to be C1. Okay. So we're going to notice that that's going to be something that's common. So the closest position, C1, the furthest position, C2 of the slider. Okay. Okay. And then stroke is going to be the difference between C1 and C2. Okay. What's the full displacement that we get as we go one rotation around in that crank? So this difference right here is the stroke. Okay. Now, when we have an inline slider crank mechanism, we can say that our stroke is going to be half. I'm sorry. I'm going to do that again. My L2, the length of my crank is going to be equal to the stroke divided by 2. Or if you wanted to, more often, we solve for the stroke and we would multiply 2 times our length of our crank. Okay. And that's the reason that is because the crank is really controlling how far out and how close this gets on this inline. So when the crank is out here and laid down in line with the connecting rod, it's going to be its furthest point out. So that's going to be here. And then when it rotates around and it gets on this side, that moves this distance. So the difference between these two is going to be 2 times the radius, or if you would, it's really the diameter of that crank, right? But it's 2 times the radius is going to be equal to what the stroke is. All right. So, so we can say that the length of L2 is going to be the stroke divided by 2. So if we know in the end what our stroke is going to be, which many times we might say, we need this to move 20 inches or 2 inches or 4 inches. Then what we can do is we can say, oh, if that's the case, if we need that to move 2 inches, then that means that our L2, the length of our crank, needs to be 2 times that stroke amount. Do you see that algebraically? So that's going to be the next thing that we put on our equation list here, okay? So in this section, I'm going to kind of start a new section here. And this is going to be for inline slider cranks. Okay. All right. We know that the stroke is going to be equal to 2 times L2, or L2 is equal to the stroke divided by 2. I like putting the stroke first and having the stroke equal to, because again, your problem statement is going to be, I need this to move a distance of. Okay, so the stroke is what you start with, and then you can use that to calculate the length of your crank. So L2 is going to be your crank length. Okay. So in any example, then that's an inline slider crank, we know that we can figure out the length of that crank by just taking whatever that output stroke needs to be divided by 2. And we got it. Okay. But then we need to determine the length of the connecting rod. Okay. So the length of the connecting rod, L3, is going to be 3 times L2. Okay. 3 times L2. So L3 is going to be the connecting rod length. Okay. So obviously, if we're dealing with inches or if we're dealing with millimeters, those would be consistent units, for whatever they would be. All right. Now, when we have an inline slider crank mechanism, our Q is going to equal 1. Okay, because remember, when we have symmetrical motion, we're going to have the same distance going in, or the same time to go out as it would be to in. So our Q is going to equal 1, and our beta is going to be equal to 0. Our imbalance angle is going to be equal to 0 because we're not offset. Okay. Betas are only going to be present when we have an offset mechanism. We have an inline mechanism. There's no offset. Okay. All right. So this is kind of like our little inline slider crank section. Okay. So what I want to do is I want to look at an example of how we would go through the design process for an inline slider crank. Okay. So that is going to be looking at problem. We're going to go to the end here. We're going to look at problem 511. Okay. Problem 511. And after this problem, we'll take a break. All right. We'll kind of see where we're at. Okay. So this is going to be the next practice problem that you're going to do for your set. I picked 511 strategically because you're going to be doing for your homework 512, which is very similar, just different numbers. All right. So this is our practice for that one. So this is going to be problem 511. Okay. Problem 511. Now, at the top here, these are the instructions for this section of problems, okay, 11 through 18. You're going to be doing for your homework 512 and 516, okay? Our first practice problem is 511. Our second practice problem is going to be 515, okay? So here it says for problems 511 through 518, design a slider crank mechanism with a time ratio of Q. Now, Q is listed for each one of these. So for number 11, Q is equal to 1, okay? So we'll identify that in just a little bit. For the stroke, which they identify as delta R, okay? And the stroke in this case is going to be 2 inches. And then the time per cycle. So they wrote this a little different, which is kind of a little irritating, but they just put T. This is going to be our delta T cycle. It's going to be, in this case, 1.2 seconds. Okay, so with those 3 variables given, they want us to graphically find the lengths of each one of the links. So we're going to find L1, L2, L3, and W2, and the speed of the crank. So we're going to do, I'm going to bring my over here. All right. So given, we know that Q is equal to 1. I'm going to say stroke. I don't like delta R. Stroke is equal to 2 inches. And our delta T cycle is equal to 1.2 seconds. Okay. That's what's given. What we need to find, okay. Now, L1, we haven't seen an offset slider crank mechanism yet. L1 is going to be associated with that. So for our problem, because our Q is 1, we know it's an inline slider crank, okay? So I'm going to say, this means that it's an inline slider crank, okay? So that means that there is no L1, okay? So if we want to identify it, we would say that L1 is equal to 0 because there is no offset from the center of rotation to the path of our slider, okay? So we're going to have to find L2, okay? And L3, okay? The length of the connecting rod. And then we are going to have to find our W of our crank, okay? And then we're going to draw it out in CAD, okay? Now, let's do a couple things here before we go to CAD, okay? So as we said earlier, our Q is equal to 1. Because our Q is equal to 1, we also know that our beta is equal to 0. We don't have this imbalance angle. That'll come into play when we have an offset slider crank mechanism. All right. So that means that we have symmetrical motion. Okay. Now, even though W of the crank is listed last, we have what we need to calculate that. So let's go ahead and calculate that because I tend to forget it otherwise. So number 2, our W of our crank is going to be equal to 1 revolution divided by our total time of one cycle, okay? Now, again, in the problem here, they did not use delta T, but on the top here, it says that this is the time per cycle T. So that's where we know that that's delta T cycle. So that value is equal to 1 revolution over 1.2 seconds, right? Now, because we're going to report our angular velocity of our crank in RPMs, we just simply need to do 60 seconds in 1 revolution. Seconds cancel. And our W of our crank is what? What do we get for that? Oh, Emily got it already. 50 RPMs. Yes. 50 RPMs. So we'll get done with that one. So that way we don't have to forget about it later or have to do it after we do everything else. Okay. Okay. So now the next thing we know, so we've got our W of our crank, so we can just cross that off. But we need to find out what are the lengths of links 2 and links 3. Okay. Now we're given our stroke of 2 inches, right? We're given our stroke of 2 inches. So if you remember from our slider crank, oopsie, wrong one here. I want to use the one that I have one already filled out. From our inline slider crank mechanism, we know that the stroke is going to be equal to 2 times the L, or our L2 is going to be half of our stroke, right? So we can rearrange that and we can say step number 3, L2 is going to be our stroke divided by 2, right? Or you can do the delta R. That's what the book uses. I just don't like delta R as a variable for stroke. So I know that my stroke is 2 inches, and I'm going to divide that by 2. So my L2 is going to be 1 inch. Okay. So when I draw this in AutoCAD, my L2, the length of my crank is going to be 1 inch. Now, if I go back, another one of the variables that we can calculate is L3, because we know that L3 is 3 times the length of L2, right? So I'm going to go back over here and we're going to say, all right, for L3 is going to be equal to 3 times L2. So that's going to be 3 times 1 inch. So my L3 is going to be 3 inches. Okay. Right. So now that's the information I need then to draw out my mechanism. So I'm going to go over to AutoCAD. Okay. And I'm going to give you some time. I do want you to draw out this mechanism in its extreme positions. So I want to show you first what I have here and what you need to add to it, or what you need for your diagram. So number 1, you'll notice that on the top here, this is this slider crank mechanism with my C1 in its closest position. Okay, so that means that my link number 3 is overlapping with link number 2, and it's over in this side over here. So notice that my center of rotation for my crank is in line with my slider. Okay, so it has to be because of our Q equal to 1. Okay, that means that it's the same stroke time out as it is in. So now this is going to rotate around, and now down here in the other extreme position where C2 is all the way out, now you're going to notice that it's in that position. Now these are in line. A is in line. The center of our crank rotation is in line from one to the next. So if I measure from C1 to C2, this is that stroke of 2 inches. Okay. And then what I did was I really laid those two out first. And then I went backwards. My distance of 3 is 3 inches, and my crank length L2 is 1 inch. So this total is 3 plus 1 is a total of 4, okay? From the center of rotation when 2 is in line and laid out with 3. Does that make sense? At the top here, this is where 2 is on the, if you would, 180-degree angle. 3 is overlapped for an inch, and now there's 2 inches left. So 3 is a total of 3 inches, but 1 inch of it is over on the left-hand side of A here, okay? Now, the labels that you see here are the labels that you need. Again, C1 is going to be in its closest position, so that's why it's called C1. C2 is when it's in its furthest position out. So what I'm going to do here is I'm going to keep this up on the screen, and I'm going to give you time to create this diagram in its 2 positions, its 2 extreme positions, and labeling the items that we see here, okay? And I'm going to stop the recording for a little bit, and you can stop it if you're watching the recording. And then when we come back, we'll kind of continue on from here and kind of do a wrap up. So I'm gonna stop or pause the recording. Okay, now that we have everything all set for example problem, I mean, it is problem, it's at the end of the chapter, but this is going to be a practice problem you're going to be handing in. So I wanted to just do a really quick review of what you're going to be handing in and what's expected for you to get full credit. So number 1, you're going to be handing in the manual work that we did, calculating the W of the crank, 50 RPMs, showing all your work here with units canceled and such. Then calculating the distances for L2 and L3, and then taking a screenshot of the arrangement where we've got the mechanism in its closest position for the slider and its outbound position, showing the difference for the stroke of 2 inches. And then I just identified here all of the points and such. So during, the time that you had to draw it, hopefully you had enough time to get that going. So screenshot of this, and then also uploading a scan of the manual work that we worked on for problem 511. Any questions at all on what to submit for this practice problem? This will be similar for the next 2 that we do as well. So since there are no questions, then what I'm going to do is we are going to go back to our PowerPoint presentation, and we're going to continue on in the chapter. So the next section here is going to be looking at a different type of a slider crank mechanism, and this is going to be one that is offset, okay? So in figure 535, actually not 535, 555, it must have been a little bit of a typo there. So if we look on page 115, you're going to see figure 5.5, and there are 3 versions of it here, okay? So I want to kind of go through this in detail so that we get the understanding of what they're showing us. So first of all, in the original diagram in part A here, they're showing this offset slider crank mechanism. Now, we know it's an offset slider crank mechanism because the center of rotation for our crank is not in line with the actual slider itself. It's not in line vertically or horizontally. It could be in line this way as well. It's not in either of those directions. It's offset. So what happens is we get a new dimension here, this dimension of L1. L1 is going to be the offset from the center of rotation to the path of the slider, okay? So we want to add that. That's going to be something that we're going to have to be aware of. So what I did was I had my inline slider crank over here, slider crank, and then I've got my offset slider crank over here. This is referring to figure 5.5, and L1 is going to be the offset, okay? And that's going to be the offset from the center of rotation to the path of the slider as we see in that figure, okay? So up until this point, we've looked at L2, which is the length of the crank, L3, which is the length of the connecting rod, but L1 is going to be the distance of the offset from the center of rotation to the path of the slider, okay? So again, L1 is our offset, and it's this dimension in this orientation as we see it right here, okay? Now, in the same illustration, we are seeing the same extreme positions, meaning we're seeing the center of that slider as point C, but they're calling this C2 in its furthest out position. And this is when we have, from the center of rotation, we have the crank and the connecting rod in line with one another so that C2 is in its furthest out position, okay? As this rotates around and it gets to the other side and we have link 3 or the connecting rod overlapping with the crank. Now this is going to be its closest position, which is going to be C1. So again, the same letters and the same links as it was in the inline, but now we're just seeing this as offsets with L1, but then using the same values of C2 and C1 being in its furthest and its closest position, okay? All right, now a couple things here. When we have an offset arrangement, okay, we know that L1 is going to be the offset, but we can also say that L1 is going to be less than L3 minus L2. So it doesn't mean that we're calculating a value for L1, but what it's saying is it has to be less than whatever the difference between L3 and L2 are, okay? I mean, L3 minus L2. It has to be less than that. So you can pick that number, okay, with that guidance. Now, if we wanted to calculate the length of link number 2, L2 is going to be equal to AC2 over 4. Now, AC2 is a distance on figure 5.5. So I want to show you that. So L2 is going to be AC2 divided by 4. Okay. So let's look at what that means, AC2. So if we look here at this diagram, A is the center of rotation of our crank, and C2 is out here. So it's the length of that line right there, okay? And we know that to be A, if you would, plus C2, because we know that L3 is 3 times L2, right? So if L2 is here and this is 3 times L2, then that's a total of 4 times L2. Does that make sense to everybody? So once we know this length, if we have this already dimensioned, and we will, then that'll give us the value that we need for L2, okay? So A, it's the length of the line from A all the way to C2, that length, okay? It would be like if you would in a line dimension. Okay. So that's how we're going to figure out the length of L2. And then using the same thing that we did earlier, we're also going to say L3 is equal to 3 times L2. So once we know what L2 is, L3 is going to be 3 times that. Okay. Now, because this is an offset slider crank mechanism, okay, kind of peek back up here. That means that we're going to have a Q that is going to be greater than 1, okay? So we can write that here. We can say Q is going to be, oopsie, not less than 1, greater than 1, okay? And we're going to have a beta of a and we're going to have a beta of some number. We're going to have to calculate what beta is. And we know beta is going to be equal to, and that's up here, 180 degrees times Q minus 1 over Q plus 1. Okay, so we are going to have a value for beta. All right, we'll have to calculate that because it's offset. Now, additionally, there are 2 other angles that we're going to need for construction. Okay, and those 2 angles, I'm going to zoom in here, are going to be this theta M and this theta N. Now, I'm going to zoom really far in so that we can see this. Now, we can kind of look at it up here. Here's the full illustration. Beta, which is the imbalance angle, is the angle that's created when we have our AC2 and our AC1. It's this angle between those two, okay? Those 2 extreme positions. Do you guys see that? Okay. So that's where beta is. So if I go down here, that's going to be where we see beta. All right, right there. Now, to construct beta, if we just try to put our 2 sliders in place for the stroke, and then we try to get beta in place, it's kind of like we don't have enough information. So there's two other angles that we need. We need theta m, which is the distance from the horizontal to AC1, okay? And then theta n is going to be the distance from the horizontal to AC2. And if we look at the geometry here, all right, what we can do is we can see a relationship where we're going to have theta n is going to be equal to theta m minus beta. Okay, so once we get beta, that's going to go down there. Now, theta m. This one is going to be something that you pick. Okay. And that's all I can really say about that. We start with a theta m, and it's going to be something that, and if you would have a design in front of you, you would have a better idea of what that angle should be. But theta m is going to be a value that you pick. And then you're going to see, does it look proportional? Does it work out? All right. And then if it doesn't, if it's too shallow, then you have to bump it up a little bit. Okay. And you'll know that when we do our design. Okay. So, so I'll walk you through that process, but you're going to be picking that value, and then you're going to calculate beta. And then n is going to be equal to taking that m minus beta. Okay. Okay. So just kind of put that in the background. So what we're going to do is we are going to work now with this set of conditions to design an offset slider crank mechanism. Okay. This is going to be our second problem that we're going to do for our practice problems. So the problem that we're going to look at the end of the chapter is going to be problem 515. Okay. So 515, you're going to notice has, and it's the same section of problem here. We're going to be given a Q of 1.37. We're given a stroke of 46 millimeters, and we're given a total cycle time of 3.4 seconds. Okay, 3.4 seconds. Now, we need to find L1, 2, and 3 and W2. Okay, so I'm going to grab a piece of paper here, and we're going to start our new example. So this is going to be problem 515. Okay. And again, this is your second practice problem for this section. We're given a Q equal to 1.37. Our stroke is equal to 46 millimeters. So we're going to be working with metric units this time. And our total time for a cycle is going to be 3.4 seconds. Okay. And those three are given to us on that same line, if you would, for problem 515. Now, what we want to find, okay, we want to find W2, L1, L2, and L3. So again, this is another slider crank. So there's not an L4. L3 is the connecting rod to the slider. Okay, just like on the last one that we looked at. But this time, we are going to have an L1. Okay. All right. So a couple things. Now, as we look back at the items here, okay, we're going to need to calculate a beta. All right. And we're going to use our Q to do that. We were given a Q of 1.37. So we want to calculate beta right away. Well, no, I'm actually gonna back up. Let's do W right away, because otherwise I always forget that. If I jump in and I start looking at the design, I forget to do W. So let's do W first, then we'll come back and we'll do beta. So step number one is going to be W2, or the angular velocity of the crank. So step number one is going to be W2. We know that to be 1 revolution per the total cycle time. Okay. We know our total cycle time is 3.4 seconds. That up a little bit. So 1 revolution for 3.4 seconds. And then I've got to convert this to RPMs. So I know that there's 60 seconds in 1 minute. Okay. Seconds cancel. So my W2, what do we get? $17.647. Yep, that looks good to me. And that's going to be RPMs, right? So we can put a box around that because that's one of the quantities that we want to calculate. So I'm going to put a little check mark up there. We've got that one done. Now we're going to calculate that beta. Okay. We know beta is equal to 180 degrees times Q1, or I'm sorry, Q minus 1 minus divided by Q plus 1. So 180 degrees times 1.37 minus 1, 1.37 plus 1. Beta. Let me know what you get for a number for beta. 28.1. Anybody else get that? Yep. Okay. Thank you, Aaron. 28.1 degrees. Perfect. Okay. All right. Now, once we have this, we're ready to kind of go to CAD, okay, and start laying this out. All right. So I'm going to go over to AutoCAD and I'm going to pull up my problem 515. Now, this is the done problem, but I'm going to walk you through this because this one's, there's a little bit more to this process than the other one. Okay. So this is going to be our end result. All right. This is going to be our end result. And you're going to notice here that I have C2 all the way out, C1 all the way in, and I've got my L1 identified here. L2 is the length of my crank, and L3 is the length of my connecting rod. Okay. 46 millimeters is my distance between, or the stroke that I'm trying to achieve. So I have this done. So we're going to go over here and I want to start with the construction and the process of, number one, getting our stroke in position. So the only thing that this problem is telling us is that we have a Q of 1.37. So we know, first of all, it's offset. It's not going to be an inline slider crank. It's going to be an offset slider crank. But we also know that the output stroke is going to be 46 millimeters. Okay. So the first thing you want to start with is going to be the stroke, because this is our end result of the motion. And then we're going to kind of work it backwards. So I drew in my 46 here. All right. Then in order to get where this center of rotation is, I need to have the intersection of where AC1 is and AC2. Okay. Now, if I go back, I'm going to go underneath here. We're going to go back to that illustration 5.5. Okay. Now, here's our C1 and here's our C2. So for our problem, this is the stroke. This is the 46 inch or 46 millimeters. Okay. Now, as we look here, our beta is the line between A to C1 and A to C2. I can't just randomly put that in, all right, because I don't have a place to start. So what I need to start with is my theta M. And this is the one that I told you earlier. We identify that. We're going to just use it, all right? We're just going to, I should say, we're going to specify it, okay? So in the problem that I did, okay, when I look back at my AutoCAD here, okay, I'm going to scooch back over here. I'm going to pan over. I used 45 degrees just to get started, okay, to see how this looked. So I started with 45 degrees. So what I do then, my process here is I want to draw the line from here up, and it is going to be at a 45-degree angle from horizontal. So I'm going to change this to my hidden line. I'm going to grab my line here, center. I'm going to make a horizontal line, kind of long, okay? I'm going to put on my, that's helpful, yeah. And then I'm going to rotate this, and I'm going to select my line. I'm going to rotate it, hit enter. The center of rotation is going to be right here. I don't want to copy this. I'm going to turn off my ortho now. I don't want to copy this because I don't want to leave a copy behind. So I'm not going to do C, but I'm going to go in a clockwise direction. So that means I need to put a negative 45. Okay, so you got to put a negative in front so it rotates clockwise in this case. So this is going to be the direction of my A to C1. All right. Now, if I go back underneath here, now I need my theta n. Okay, because I can't put this in here and go right through the C2. So what I'm going to do is I'm going to put in my theta n, and then I'll be able to find the intersection so that we can see that beta comes in there. But we're going to use beta for it. So if you recall, from the bottom of this section where I've got the offset slider crank, theta n is going to be equal to theta m, which was the 45 degrees that I just picked, minus my beta. And I calculated beta to be 28. So my step number 3 here, I'm going to use theta n equal to theta m minus beta. So this is going to be 45 degrees minus 28.1. You pick the 45 degrees, okay? You could pick 40 degrees. You could pick 30 degrees. You could pick, and again, you're going to have a better feel for it if you had an exact application in mind. We're just given some numbers here, so you've got some latitude for that number, for that theta m. Starting with 40, 45 degrees, good place to start, okay? And just see if it works out. All right, so my theta n, what do we get for a value for theta n then? 16.9, okay, degrees. All right, so now I'm going to use this number, and that's going to be, in AutoCAD, I'm going to use, I think I'll use the object line for this one. Through here, I'm going to make it horizontal. Okay, long enough so that I can get an intersection. And then I'm going to rotate this again. Oopsie. Rotate. I'm going to select that line. Its center of rotation is going to be back here at C2. And here again, I want to go in a clockwise direction. So I'm going to do negative 16.9, enter. And now this is the intersection where my A is going to be. Okay. And if I do my measurement, a dimension, an angle dimension right here between this and this is going to come out to be, how come 27.47? Did I put the wrong number in? Good. So 45 minus 28.1. Maybe I put this in wrong. Hold on. I'll do it again. Oopsie. From horizontal, rotate, negative 16.9. Make sure it's entered. Let me see, it should come out. Unless we did the math wrong. Oh, there it is. I must have keyed in something other than 16.9. Okay, now it's coming out. So this is my beta angle right here. Now, the center of that intersection is where the center of my crank is going to be. So if I go back over here, that is going to be where you put your symbol for your frame and point A. Okay, so I'm going to copy that over to my location over there. I'm going to go from that center. I'm going to put that right here at the intersection that I just created. Come on. Try that again. Copy from the center to the intersection. There we go. Subtract it. Okay. So that's where that's going to be. Okay. Did everybody get that in place so far? All right, so you've got your 46 millimeters apart. You've got your point A, the intersection here for C1, C2, and you've got your imbalance angle of 29.1, or I'm sorry, 28.1. Okay. Now, I'm going to go back underneath. We need to calculate the distances for L1, L2, and L3. All right. Well, L1, we actually just got, and we just need to measure it. So we're going to go back to AutoCAD. Okay. And our L1 is going to be the vertical distance between the center of rotation and the center of the path for our slider. Okay. So this distance right here, 20.1, is my L1. All right. So that's going to be measured from CAD. So I can put underneath here, step number 4, and I'm going to say CAD, L1 equals 20.1 millimeters. Okay. So that's one of the distances I got. So I can say L1 is done and W2 is done. Okay. So everybody see how we got that? The offset is from the center of rotation to the path that that slider takes. Okay. And everybody understand the theta N, theta M, and beta? Okay, so now we need to figure out the lengths of L2 and L3. Now, actually go back underneath. If you recall, we're going to take L2 is going to be equal to AC2 divided by 4. Okay, AC2 divided by 4. So we need to measure that length. So if we go back to AutoCAD, A to C2, we need to measure along that line. So we're going to do an aligned dimension from the center of A to the center of C2. You're going to get 69.1, or you should get something very, very close to that. Okay. So if I go underneath, L2 is going to be AC2 divided by 2. This is 69.1 millimeters. I'm sorry, not divided by 2, divided by 4, divided by 4, divided by 4. So my L2, what do we get? 17.275. That sounds good. 17.275 millimeters. Okay. Now we're going to use this. And we're going to go back to AutoCAD. Okay. And now you're going to draw a circle with a radius of 17.275. Okay. Now, this is where the intersection is for point B. So this would be a joint from the intersection of where the radius crosses. Shoots, I knew it. Don't have the right object snaps on. I got to go in here closer. So I'm going to go from this intersection and right about there. Okay, so that's going to be point B. And this is going to be what we call B2 because it's on its position all the way out along that line. Okay, so this is going to be B2. Okay, so we always call the end of the crank B, right? A is going to be the center of our rotation of our crank. B is going to be the radius of that crank. And then C is going to be the endpoint of the connecting rod. Okay. Now you can get rid of this radius here. Yeah, I'm going to leave it for right now because then I can put that same point, that same joint from here up to this intersection. Okay. And that's going to be actually B1. Okay. So that's going to be where it crosses over and it's going to be in line with C1 where it overlaps. So then I can trim away the extra length here, and then I can get rid of that radius. And then I can trim this to center here. So that's what I have so far. Now, as far as dimensions, so I'm going to grab my dimension here. This is going to be an aligned dimension from the center of A to the center of B here. That's the 17.3, and that's the length of L2, right? I have it rounded, so 17.275 like we put in, okay? And then the length of L3 is going to be the length right here, right, of link number 3. So I'm going to do another aligned dimension, okay? And that should be, and it will be, 51.8. But if we take 17.275, go back underneath here, L3 is going to be 3 times L2, which is going to be 3 times 17.275 millimeters. Our L3 to a couple more decimal places should be very close to the number that we got. What do you guys get for L3? It's going to be 50. What was it in CAD? I had it to 51.8, but we should get 51.7825. Yep. Millimeters. And that makes sense because again, we used the values. So now we've got L2, we've got L3. Okay. And then we have it confirmed on our CAD. Okay. The only thing you want to do is add a couple of labels here. Okay. And a couple of labels are going to be like on here, this would be L1 is equal to, and that's going to be the 20.1. Okay. And then over here, I'm going to copy that L1 is equal to, and this is going to be my L2 is equal to, and it's the 17.3. And then I'm going to, copy L2 equals to over here, and this is going to be L3 is equal to. And then that way you can see that the values that you calculated come out in CAD here. And then you have to have your beta identified, so don't forget this angle. And then also add in the angles for theta M. And theta N. So we get 16.9 there. Because I want to see that from your calculations that we can, we can make sense of the values that you have here. So I'll compare those here, something like that. So all the numbers you use to either calculate or determine values you want to show on the diagram here. Okay. Remembering that the 45-degree angle was not given to us in the problem. That was something that I chose. Again, right around 40 degrees is a good number for like horizontal problems like this, 30, 40, 45, you know, and they will then provide that quick return action like we saw here. All right. So any questions on the diagram here? What I'm going to do is I'm going to go back underneath my camera. So to hand in for the practice problems, this is your third problem for 515, the work that we showed here. Okay, all of the items here is showing all the work. And then the numbers that we see here, you should have all of those labeled on your diagram here so we can make, if you would, make sense of the two positions utilizing the items that you see. So making sure that you have your C1 and your C2 labeled, your A labeled, your B1, your B2, the lengths of A to C2, the length of L2, the length of L3, the length of L1, okay? And then the stroke and the beta and the theta M and the theta N, all the ones that you see here. This is what you want to duplicate and make sure that you get the same values, okay? So this would be the screenshot to accompany problem 515, okay? Now, as far as we went today, I'm going to go back underneath our camera. And if we go to the end of the chapter there where those problems are, okay, you would be ready to do the following problems. You're assigned 5.2 and 5.4. These do not require any sort of diagram. You don't have to do any CAD for the first two, okay? These are your first two homework problems. These two are going to be like that first example that we did, just practicing using the equations for Q, beta, W, that kind of thing, okay? But then the homework problem that you have assigned is 512, which is going to be just like 511, but different numbers, okay? And then the homework problem that you have assigned is 516, which is just like 515, which we just did. The requirements for handing in for each of those problems are what we just talked about for the practice problems for each one of those. So the handwork you have to have scanned in, and then you're going to do a screenshot for the diagrams, identifying all the different, you know, elements, the letters for the joints, the lengths of each one of the links that are required here and such. Okay, so use those practice problems as your guide to what to hand in. Okay, now you do have one more homework problem and one more practice problem. We will go over that, and those are going to be crank rocker mechanism. And we'll go over that the next time we get together. So the next time we get together, we'll finish up our last practice problem, and then you'll be ready to start that last homework problem. Okay? So that's as far as I'm going to go today. Does anybody have any questions before I let you go? Okay, so then what I'm going to do is I'm going to stop the recording here. Okay.